Okay, this is the time in the semester where we transition from differential calculus and we're going to start doing integral calculus. And the way that we introduce integral calculus is by defining what we like to call, oops, I don't know why that happened there. That was weird. The area problem. All right, and it's a very simple problem when you sit back and think about it. So I'm going to be using one of the examples out of your book because it's a nice picture and everything, and my drawing or my artistic abilities are subpar, to say the least. But anyways, here we have S, and S is a region defined by any point x comma y such that x is in between a and b inclusively, and y is in between 0 and f of x inclusively. So that's what defines this region S. Now, the big question that I have for you is, what is the area of this region? Okay. Now, when you think about this, okay, we really need to think about, well, what do we mean by area? Now, obviously, area is the shaded region. I'm going to shade this for us underneath this curve right here, okay? But here's the problem with this. This is a curve. And if we're interested in the area under the curve, we really don't know too much about areas other than some very rigid objects. For example, if I asked you what is the area of this graph, all right, which we call this in statistics, we call this a uniform distribution. All right. Let me space that out a little bit more evenly here. There we go. So this is 1, 2, and obviously this would be 3. And this would be 1 and 2. If I asked you to find the area of this, what we could say is, well, the length here is 3. The height here, obviously, is 2. So the area of this uniform distribution would be 2 times 3, which equals 6 units squared. Now, why can we do this so easily? This is a nice rigid object. And we actually have a formula here that actually demonstrates how we find area of a rectangle. All right. Now, other times you may even get luckier. You may get something like this. All right, which is nothing more than just a triangle. All right, but what we know is that if we know the height and the base, the area of a triangle is 1/2 base times height. I mean, you can even derive this formula. You can derive the formula just by looking at a rectangle. If I label this base and height, we know for a rectangle, area equals base times height. But if I were to cut this in half, notice you get this beautiful right triangle, so just cut it in half. There's your area for a triangle. I mean, you can easily derive these just by kind of working off of one simple one, which is the rectangle. Which should lead us into at least a little bit of intuition, which says, if I wanted to find the area under this curve right here, all right, well, we can go ahead and we can kind of estimate what this area is. And to do that, we're just going to create a bunch of rectangles, all right? So what I mean by that is this. Let's say, for example, you wanted to break this up into 4 rectangles. Here's region 1, 2, and 3 respectively. Well, I can go ahead and just create little rectangles here, and they have a very special name, and I'm going to tell you them in a little bit. But notice here, I can find the area of those rectangles right there, okay? Now, obviously, we're not getting the actual area of this, and that's okay. This is going to give us an approximation of what this area is. Because what we know is that this distance for each one of these rectangles is going to be nothing more than just the distance of b minus a. And since we have 4 rectangles, we're going to divide it by 4. We call this our change in x. Okay? Next, we know the height of every single one of these rectangles. So let me get out a different color marker here. So for example, the height of this rectangle right here will happen at that point where it touches my function. So the height of this specific rectangle, I'm just going to call it f of x1. And the height of the second rectangle is right there. So I'm going to call that f of x2. And notice that the height of every single rectangle is a little bit different. But the key in the understanding here is that the height always touches my function. So this is going to give us an approximation. And in fact, it's going to give us, which is okay, it'll give us an under approximation. All right? And that's okay because, like I said, we are looking for the area underneath the curve. But we don't have a formula. Sorry, I'm just going to rewrite this because I like the way this looks. All right. So we don't have a formula for this specific shape, but we can approximate it, okay? Now, there's a lot of things going on here. So let's take a step back, all right? And I'm going to erase some stuff, but I want to focus on just one of these rectangles here for a second. So just give me a little second here. I'm just going to erase this. All right. And I'm going to focus on this rectangle right here, right in the middle. Here we go. All right, so remember, we said that the distance, x, is right here. It's going to be b minus a divided by 4, whatever a and b are, we can find that distance. And the height, and we're going to call this f of xi, meaning just some y value within this interval, okay? Well, if we wanted to find this area, all we would have to do is say, well, the area is going to equal delta x multiplied by f of xi. This is what we call an under approximation, or we call these right-ended rectangles, okay? Or right endpoint rectangles. And that is because the right side of the rectangle is touching our graph, all right? It's touching our curve. We could do the same thing with the opposite side. Now, the opposite of right, obviously, is left. So let me go ahead and let me draw what left endpoints would look like for us. And you're going to notice something here. And then I got a nice little demonstration I'm going to show you. So let me change my color. I'm going to use blue. So if I'm going to use the same exact spacing, delta x equals b minus a over 4, and I want my function to touch the left side, or my rectangles to touch the left side of the curve, here's my first curve. I'm sorry, here's my first rectangle. Here's my second. Here's my third. And here's my fourth. All right. So notice by using left end rectangles are over approximation. What we're going to find is that the area of this is going to be a little bit larger than what the area should be. But in reality, when I bring both of these together, oops, sorry, I'm confusing myself a little bit. There we go. So I know this looks a little confusing initially, but here's, at the end of the day, here's what's happening. The true area, actually, let me write it in black. The true area for this region S is going to lie somewhere in between the area of the over approximations and then the area of the under approximations. All right? So another way to think about that would be the area of the left endpoints. Actually, I got it backwards. The area of the right endpoints and the area of the left endpoints. Now, you know me. I love Desmos. So I'm going to go ahead and show us a nice visual representation of what's happening here. Okay? So give me a second and let me pull this up. So the big question now is, well, how do you actually do this? All right. So I have an example here. All right, nice little graph here. And what we're going to do is we're going to be finding, so we're going to use, marker's way too thick. Hold on one sec. I'm sorry. So we're going to use 5 rectangles to find a lower estimate and an upper estimate. So we have two separate problems here. For the area under, under the curve from x equals 0 to x equals 10. All right. So we're going to sketch each one of these, and we're just going to go ahead and do this. All right. And it's not difficult at all. All right. And the name of the process that we're actually using here, it's called Riemann Sums. Now, I'm not going to go too far into the Riemann sum thing because there's a lot of sigma notation and everything, and I don't know how familiar we are with that. So we're just going to kind of bypass it, but we're only going to do this, and then we're going to learn a bunch of formulas that actually help us do this, all right? So the first thing we need to do, all right, is we need to look at this. We know we start at 0. We know we're going to 10. So you got to be careful here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, all right? And we want 5 rectangles. So our delta x here is going to be 10 minus 0 divided by 5, which is 2. And what that means is for every 2, we're going to draw a rectangle for us. So our delta x, this distance right here, maybe I should use a different color so you could really see it. This distance right here is that delta x I was talking about, and this is going to equal 2. All right? So the first thing we want to do is a lower estimate, okay? So a lower estimate means write endpoints. Let me write that here. And the reason why I know it's going to be right endpoints is because since my delta x is 2, I want all of my rectangles to be below the curve. So here's my first. Here's my second. Here's my third. Here's my fourth. And there's my 5th rectangle right there. All right, now, to get, and I'm going to use just some notation here. So to find the area of the rights, notice that we have regions 1, region 2, 3, 4, and 5. Okay? Now, I need to find the area of every single one of these rectangles that we just drew, okay? And it looks like we're going to have to estimate a little bit here, and that's going to be absolutely fine because remember, this is just an estimate anyways, all right? So the first rectangle is going to be delta x times f of x1. Our second rectangle is going to be delta x times f of x2. And then we just keep repeating this process for each region that we have. And you are going to be thanking me once I show you the formulas for all this stuff, because it is a lot of writing initially, but I guess you have to appreciate what Archimedes did for area under the curve. And yes, I said Archimedes and not Newton, because there's tons of literature that supports that Archimedes was actually finding areas underneath a curve well before Sir Isaac Newton and Leibniz started talking about calculus, but more on that later. So anyways, if you notice here, every single one of these terms has a delta x in common. So I'm just going to go ahead and factor out my delta x. All right, and then finally, we know delta x was 2. So all we're going to do is just zoom out, and we're going to approximate each one of these heights for us here. So the first one is pretty simple. I think that is 3. Plus the second one, it's a little bit under 2, so we'll say 1.8. For 3, it's a little bit under 1, so we'll call that 0.8. For 4, that is definitely well below 1, so we'll call it 0.25. And then for for 10, all right, it's on the x, well, it's really near the x-axis, so I'm just going to call it 0. So all I'm going to do here is just grab my calculator, add it up, and multiply by 2. So when I add this up, I came up with 5.85. And then when I take 5.85 and multiply it by 2, come on, why does it do that all the time? So when I add everything up and I multiply by 2, I get approximately 11.7, which we could just say is 12. Now we do the right or the left endpoints or the over approximations the same exact way. Now, the one thing I'm not going to do is I'm not going to go ahead and demonstrate all of my algebra and everything here, all right? Because it is literally the exact same thing. But I will write it in a different color for us just so we can follow along. So up above, let me write left first. It's going to be delta x times f of x1 plus f of x2 plus f of x3 plus f of x4. All right. So what I am going to do is I'm going to scroll back up. I'm going to erase all this. All right. And then I'm just going to go ahead and draw my rectangles again. So there's 2, 4, 6, 8, and 10. And we want the left end rectangle. So this is going to be the upper or over approximations. So I want the left-hand side of my rectangle to touch our curve. So here's my first region. Here's my second region. Here's my, here's my third region. Need to get a little bit cleaner with that. There we go. That looks better. All right, here's my fourth. And finally, here's my fifth. All right, so there's R1, R2, R3, R4, and R5. Now, scroll out. Let me see if I can scroll out just a little bit more. Sorry if it's getting really small on your screen. Our area on the left is going to be 2 times. Now, we're just going to go through and we're going to look at each one of these. The first one, definitely going to be 5. For region 2, 3. For region 3, it's a little bit under 2, so let's call it 2.8. For region 4, it's a little bit under 1, so we'll call it 1.8. And then for region 5, we're going to call that 0.25. Now I'm going to zoom in. The area of the left is going to be, if I take my calculator and just add all this up, Give me 1 second, because I'm just doing this on my calculator. I get 2 times 12.85. And when you take 2 times 12.85, you get approximately 25.7. And I'm going to actually round this down because since I know it's an over approximation, I'm just going to call it 25. All right? And finally, with confidence, we can say that the area underneath the curve, the true area underneath this curve that we have, is going to be somewhere in between an upper limit of 25 and a lower limit of 12. So it's somewhere in between 12 and 25, which hopefully you're sitting there thinking to yourself, well, that's not a pretty good estimation. And I agree with you. However, we've only used 5 rectangles. If we use 10 or 100 or 1,000 or 1,000,000, these endpoints would get closer and closer and closer, and you would start to converge, or you would start to sandwich the actual true area in between the upper and lower bounds that we have here. All right? Now, I know mathematically, this is not difficult at all. I mean, the algebra associated with it is not difficult at all. However, it's the theory, it's the understanding of what we're doing behind this that means everything for us. All right? And so far, we haven't used any calculus, but we're going to use calculus very soon. But this problem right here that we just did, all right, is a very abstract math example. All right? The question should be, all right, what's the application of this? And that leads us into this topic right here. So the application of this, and it's a very common one that we've seen previously in this semester, is the distance problem. All right? So if we go back and I asked you to define distance for me, hopefully you would say, well, the distance is the amount of units that an object travels in between 2 points. All right? And I would say, yeah, that's great. Is there a formula for distance? And hopefully you're sitting there thinking, well, distance equals our velocity multiplied by time. And then I would go, well, doesn't that look like something to you? And hopefully you're sitting there thinking, well, yeah, this is nothing more than just the area, which is equal to height times length. So in other words, if I gave you some sort of curve, all right, the x-axis will be time. The y-axis is going to be the distance with respect to time, all right? And let's say you were like driving a car from your house to, I don't know, Target or Walmart or whatever, Taco Bell. I'm really thinking about driving to McDonald's right now because I want some chicken nuggets really bad. But anyways, that's me. But here's what I do know. I do know that my velocity is not going to be constant. My velocity is not going to be constant the whole time. There are stop signs. There are curves, all right, that I got to go around. I got to drive my car around. So what's going to end up happening here is my velocity may look something like this. So you know what? I'm not going to make this d of t. Let's make it v of t. That's what I should have done. So my velocity at time 0, I'm at my house, and then all of a sudden, I hit the gas, and it may look something like this as I'm driving to McDonald's, all right? Notice that my velocity is increasing here. My velocity is at 0 here, which means I could have been at a stoplight or stop sign. Then my velocity went down here or something like that, all right? I mean, there's all these things that are happening here. But here's what we know. We know that if I asked you to find the area underneath this curve from A to B, you would start to draw little rectangles for me. All right, these are going to be right end. you would start to draw these rectangles for me. And each one of these rectangles has the formula area equals height times length. Well, our length is going to be our change in time. Our height is going to be the velocity at any time t. And when we find the area for each one of those rectangles, we're actually calculating the distance traveled every single interval. And that is unbelievably powerful for us. All right? Another application for this is work. Work is defined as force, multiplied by distance. But if you take a step back and you look at this, this is nothing more than area equals the height, in other words, how much force, times the length, or as you applied that force, how far did this object move? So area equals length, or height times length again, which we can think of that as work equals force times distance. So you can find all this stuff just by finding the area underneath the curve. All right. Now what I'm going to do is I'm going to do a distance problem for us just to show us how it works. All right. So here's our distance problem. It's very straightforward. Suppose the odometer on our car is broken and we want to just estimate the distance traveled over a 30-second time interval. So below we have a recording. So at time 0, the velocity is 25 feet per second. Now you got to be careful because if this velocity is in miles per hour, all right, if that's how we give it to you, make sure you read the question because you may have to convert to feet per second. All right, so just be aware of that. But below our recording, so at time equals 0, our velocity is 25 feet per second. At time equals 5 seconds, our velocity is 31 feet per second, and so forth. All right. What we want to do is just find the total distance traveled. All right. Now, the hard part about this, all right, is notice that our velocity is never constant. See, if our velocity was constant, then we would just say distance equals velocity times time. We've been traveling for 30 seconds times the velocity, and then we'd call it a day. However, our velocity here, it's constantly changing. So what I did is I went ahead and graphed it. And as we can see here, all right, we have a function or a curve that is constantly changing. All right. Now, if we wanted to, we can do this any way that we want. But the problem here says we want to estimate the distance traveled over a 30-second time interval. And notice that the time interval is always 5 seconds. Now, if we relate distance equals velocity multiplied by time, if we relate this back to something we know, which is the area under the curve, the area under the curve is just going to equal our velocity, which is going to be the height, multiplied by, in this case, it's going to be delta t, which is our change in time. So the area is nothing more than just the velocity multiplied by, in this case, delta t is going to be 5. So all we have to do here is just take each one of our velocity readings, multiply it by 5, and then add them all up. It's very simple, all right? And I think hopefully now it's simple because you can see how this application works. The area under the curve represents a bunch of different stuff. It can be distance, it can be work, it could be anything where you have two different quantities being multiplied, all right? So for us, let's just go ahead and let's just do this real quick, all right? All right, so the area, and we just got to be careful. We got to think about this, all right? So the area is going to be 5 times. Now, when you look at all of these right here, all right, notice you have the interval from 0 to 5, 5 to 10, 10 to 15, 15 to 20, and so forth. So it's going to be 5 times 25 plus 31 plus 35 plus 43 plus 47 plus 45, because at the very end, at 30 seconds, you're traveling 41 feet per second. However, that's the end of the interval. All right. So all we're going to do here is just take our calculator. And sorry, give me 1 second here. I'm going to pause this and add this up. So we're going to get 5 times 226. And 5 times 226 is our area equals 1,130. However, we know this is an estimation of our distance. So the distance traveled is approximately 1,130 feet. Now, obviously, we could get a more precise answer if we actually took closer time intervals. So maybe instead of it doing every 5 seconds, we did it every 2 seconds, or every 1 second, or every half second, and so forth. But if you can understand this basic concept that the area under the curve is related to distance or work, and how do we find the area underneath this curve by drawing rectangles, whether they're left end rectangles or right end rectangles, you're going to be absolutely fine for this first section. All right.